In this video, we're going to talk about linear and angular speed. Now, to do this, we're going to start off with a topic that you've seen since probably first grade, for a long time at least. There should be one equation, mathematical equation, that you remember from a very early time, and that is how to relate distance, rate, and time. Distance is equal to rate times time. In this video, what we want to study is speed. Two different types of speed, linear speed and angular speed. But if we want the speed, we need to isolate this variable r, and we do that by dividing off the t. So r would be equal to the distance over the time. And of course, we could rearrange this equation for any piece that we want, but this is a basic piece that we want to solve for with linear and angular speed. We want the rate. If we think about a linear speed, what we are thinking about is how far do we travel from point A to point B. We don't really care about the twists and turns to get there, or if we're thinking about making a circular path, right? If we're making this circular path, what we're doing is essentially taking this circle and we're spreading it out over a straight line. We're saying, all right, how far did we travel as we went along the circle? So just kind of straightening all of this out. And so that linear speed, we denote with the variable v for velocity. And so that linear speed is equal to the distance over the time. But what is that distance really? If we're thinking about going around in a circle, the distance traveled along that x curve of the circle is really talking about the arc. And so we're going to replace that variable d with s for the arc length. Remember that arc length does have to be arc length we can find as s is equal to theta r, where theta has to be in terms of radians. It's the same formula that we've known forever and ever. It's just we're giving these more precise terms now. Just how do we define that distance? We define it in terms of an arc length. The angular speed. The angular speed is looking at through which angle do we travel with time. To show that it is different than linear speed, we don't want to just use the same variable v. We use the Greek letter omega, which kind of looks like the cursive W. But that is the Greek letter omega. And the angular speed is also equal to the distance over the time. If we think about the distance traveled here, if we're thinking about the angle, it is the angle. It's the theta, and we're going to divide by time. So these are the two formulas that we need to be using, but it really is just the same formula you've known for a very, very long time now. Just this d, we're defining in one of two ways. The actual distance traveled, the arc, or the angle traveled, the theta. All right, so let's take our first example. Ferris wheel with a radius of 50 feet turns through an angle of 20 degrees in 15 seconds. What is the linear speed and what is the angular speed? So obviously, Ferris wheel, we have a circle, and it is turning through an angle of 20 degrees in 15 seconds. So a very small angle here through which it's turned in 15 seconds. Start with linear speed. Actually, the more challenging answer to find in this case, but we'll do it anyways. Problem asked for it first. So linear speed, remember, we find v is equal to the arc length s over the time t. So right away we recognize that we have to find the arc length. And arc length is equal to theta times r, but remember theta must be in terms of radians. That is always true for arc length. So we need to take this 20 degrees and we need to convert it over to radians. And the way we do that, because we're starting with the degree on top, we put the degrees on the bottom, the 180, and the pi radians goes on top. That would allow the degrees to cancel. You can also cancel out the zeros, and 2 goes into 18 9 times. So we get s is equal to pi over 9 times the radius, which was 50. So arc length equal to 50 pi over 9, whatever that is, right? And the units here would be feet, and we know that because our radius was in terms of feet. So we were after the linear speed, and so to find that we have to take the arc length, 50 pi divided by 9, and we have to divide it by the time, by the 15 seconds. And so when we do that, we want to type this in the calculator. We want to be very careful that everything in the numerator goes in parentheses, everything in the denominator goes in parentheses. So we'll type in our 50 pi over 9 divided by the 15. And so when we do that, I believe we get an answer of 1.16, and our units there would be feet per second. So every second you're traveling 1.16 feet. We also wanted to know the angular speed. Remember, angular speed we denote with that Greek letter, omega. And we want to take our angle and divide it by the time. Well, here we were actually pretty much given this, right? We were given very directly the angle was 20 degrees and the time was 15 seconds. So we can just take the 20 degrees and divide it by the 15. And so when we do that, we're going to get the 1.3 repeating around at 2 decimal places. That'd be degrees per second. We're just kind of simplifying that original original angular speed that was given to us. But we were given the angular speed. We were given the 20 degrees per 15 seconds. All I did here is simplify it. Now you might be saying, well, wait a minute. I thought with arc length we were always supposed to use radians. Why do we use degrees over here? And for arc length we absolutely do, because arc length is based around this idea of a radian. Radian is defined very directly with those two things are linked very directly. With our angular speed, it's this angle through which we're traveling over the time. And so we can define that angle in any way. If we wanted to use the radians instead, if we wanted to define it as pi over 9 over 15, that's fine. It's just when we get that answer, we're going to have to make sure that we define it in terms of radians. So let me very quickly see what we get there. So we get approximately 0.02327, but that'd be radians per second. And so both of these are the correct answer, depending on what we're asked for, right? That problem might specify which one it wants, but we have to make sure that we are labeling our answer. As long as we do that, both are correct. Let's take another example. A car wheel has a diameter of 40 inches, makes 35 full revolutions in 1 minute. How far will the car travel? Again, we're dealing with a circular wheel. We're not using square ones anymore. We know the diameter is 40 inches, and we're told it makes 35 full revolutions. So we're not given the angle directly here, but it's not hard to find. Also notice we're asked to find how far the car will travel. What we're trying to do is figure out, as that wheel is spinning around, how much distance are we traveling? And that is dictated by every spot the tire touches. We're assuming it's not slipping. Assuming we're not throwing on the brakes and sliding. Every part the tire touches on the road, that is a distance traveled. So we are looking for a linear speed. To get that linear speed, we need to start by finding the arc length. So let's find the arc length. The arc length is equal to theta times r. Again, we're not given the theta directly, but we're told 35 full revolutions. We know a full revolution is 2 pi. I do want to use the 2 pi, not 360, because we need to make sure that we're using radians. And so for our arc length, we would have 35 full revolutions of 2 pi radians. And then the radius, well, the diameter was 40, so the radius has to be 20. And so we multiply all this together, 7140 pi. 1,400 pi. And so now we're going to take that, and for our linear speed, velocity is equal to the arc length divided by the time, which it was just 1 minute. We know that these were inches. And so when we divide that by the 1, of course, we're just going to get the 1,400 pi. And so let me type that into my calculator. And we should get approximately 4,398.22 inches. And linear speed is just that measure of distance. And so that would be our answer in inches. Maybe it would be worthwhile to convert this to feet, depending on what the problem asked for. Obviously, a little hard to picture what 4,000 300 inches would be. So maybe we'll want to convert that over to feet, or we might have to do some other conversions. But that is how we apply our linear speed formula.